Okay, so today we're gonna hopefully finish, well, not hopefully, we're going to finish 3.1. We have a few more questions to hit on with the verse and gas laws, and then we're gonna move on to something completely different with atomic masses. Just a reminder, your homeworks are up for 3.1 and they are hit 3.2 is now up. So while things are the most fresh in your mind, I highly recommend getting the homework questions out of the way now. So as we get closer to the exam, we can focus on more efficient study for the third exam. I'm still working on your next quiz. I have most of it already done, but it will be available to you on Friday. I'll put that up there on Friday. Before I get started, are there any questions? No? Awesome. Okay. Last class, we talked about two different equations that were used to answer gas laws. One of them was a common gas law equation. One of them was the ideal gas law equation. So one of them was the P1V1 over T1 equals P2V2 over T2. And the other equation was PV equals nRT. So these problems are really for us to decide which one to use and then how to use it. Reminder, if you are given two of something, like two pressures or two temperatures or two volumes, you need to use the common gas law equation. But if you're given only one of something, of everything, that'll be the ideal gas law equation. So if I give you those equations, do you know how to use it and when to use them? So let's look at this equation. I do want to point out that as we get further on in chemistry, some things are going to be relevant to the question itself, but not relevant to how we solve for it. So this question kind of gives you that. It says a balloon used for underwater salvage is inflated to 50 liters at a depth of 200 feet, where the pressure is 6.89 atmosphere and the temperature is 3 degrees Celsius. The balloon rises to the surface, which is 22 degrees Celsius and 0.988 atmosphere. What is the new volume of the balloon? We've been discussing gas laws. Have we discussed distance, like using feet at all in any of these equations? No. So they threw that in there because, yeah, it's important to the question itself to establish what's going on, but you want to make sure that you are comfortable with what these questions are about. So you don't accidentally try to throw that number in there and try to do math with things that are not relevant to the equation. So sometimes they'll give you a temperature when you don't need a temperature. Sometimes they'll give you just random things in there, but we need to understand that 200 feet is not necessary for gas law equations. It's just relevant to the question. We're going to continue using first, V for variable, E for equation, R for rearrange, S for substitute and solve, and E for evaluate. So we're going to kind of use the verse method here. So first, write out your variables. When I say like the ones and twos, usually I use my before as my ones and then my after as my twos. So typically what I'm solving for is my twos. But it really just depends on how you set it up. If you were to flip-flop that, it's fine. You get the right answer anyway, as long as you know this belongs to the 2, this belongs to the 1. The equation I need is P1V1 over T1 equals P2V2 over T2. I know I need this equation and not the other one because I was given 2 pressures, 2 temperatures, and 1 volume. So I'm looking for one of these volumes. So that would be E for verse, E. The V for verse would be variables. So P1 would be at 6.89 atmospheres. V1 would be 50 liters. And T1 equals 3 degrees Celsius. Do you remember what we discussed on Monday about temperature? It has to be in Kelvin. You cannot leave it at 3. So to do that, I have to add 273.15. Next, I got my 2's. My P2 will equal 0.988 atmosphere. My V2 I do not know. And my T2 equals 22 degrees Celsius plus 273.5. And that's 298.15. Let me just double check. 925, yeah. Thank you. So that's my V. My E we already have up top, my equation. My R is rearrange. So when you do this, you can either rearrange this using the letters if you feel more comfortable doing that, where, you know, get rid of the T over here, move it over here, and then you get rid of the P2. That's one way you can rearrange it. You can also rearrange it by adding those numbers in and solving for what's missing. So that's what I'll do here. So it'll be 6.89 atmospheres times 50 liters divided by 276.15 Kelvin equals 0.988 atmosphere E2 divided by 295.15 Kelvin. That's one way you can do it. So you can either rearrange with these numbers where, you know, what you could do is multiply by the temperature on both sides and then divide by 0.988, or I believe you could just divide by this number altogether. I'm going to simplify it real quick just to show you what I mean, where I'm going to solve for this by itself. And then you can just divide this on both sides. If you are very comfortable within your calculator, you don't have to break it up into 2 steps. You can do it all at once. It just depends on how comfortable you are and making sure that you do the right order. And I got 372.67. So I'm just gonna round that to 373. Do that up here. I also want to point out that those units do cancel. So if you have a liter, not liters do not, the atmospheres will cancel and the kelvins will cancel when you do all that math out. So you're going to be left in the units that your volume was originally. So it'll be 373 liters. Double check my math and make sure that you are also able to calculate this. So we already did the V, E, R, and S, substitute and solve. The last thing you always want to hit on before you move on is the last E, evaluate. So let's kind of review what we discussed last class, where we know that pressure is inversely proportional to volume, and volume and temperature, temperature is directly proportional to volume, right? So you can pick either or of these to make this evaluate work. So I think to me, the easiest one's temperature. So volume and temperature are proportional. As one goes up, the other goes up. Look at T1 to T2. What's happening to temperature? It rises. It's getting bigger. So our volume needs to also get bigger. So I know I did I might not 100% have done my math right, but I know I'm on the right track if my volume 2 is bigger than my volume 1. So 50 to 373 makes sense. That's the evaluate. Okay, I know it's supposed to be bigger. My number is bigger, so that definitely makes sense. If I was to focus on pressure, they're inversely proportional. So as pressure goes up, volume goes down. As pressure goes down, volume goes up. Look at P1 to P2. What's happening? Pressure is going up or down? Pressure is going down. Volume must do the opposite because it's inversely proportional. So volume has to go up. So that's the evaluate, is use your qualitative knowledge to help make sure you're on the right track, because this will give you a better opportunity to make sure your numbers are right, your answers are right, truly understanding what those expectations are. And it'll help you catch those math mistakes. Lastly, I do want to simplify if you did want to rearrange using the letters. I want to just show you the algebra real quick, just to make sure we're on the right track. And I know algebra can be it can be quite easy when you're doing one thing, but when you're doing multiple, it gets a little difficult. If I have P1 V1 over T1, and I want to isolate V2, the first thing I could do is multiply by T2 on both sides. That way these T2 cancel, and I now can simplify this equation to be P1 V1. Is this T2 going to be in the numerator or the denominator? Numerator, because I multiplied it. That'll be P2 divided by T1. The next step is going to be to divide by P2 on both sides. Is P2 going to be in the numerator or the denominator? As I'm dividing, the P2 will go next to the T1. So the rearrange would look like this. If you prefer to rearrange with letters, definitely always go ahead and do that. If you prefer to rearrange with numbers, that will also help you and get you to the right answer. So you kind of have to pick what works best for you. And if this was a short answer portion of an exam, you wouldn't lose points doing either way, as long as I saw some rearrangement or some like direction there. Majority of the time, there'll be multiple choice questions, so you don't have to prove it to me, but you still need to be able to get the right answer in the end. Any questions on this before we move on? All right. Let's do example 3. A syringe holds a 25 milliliter sample of argon gas at 22 degrees Celsius. If the syringe is placed into a freezer at negative 18 degrees Celsius, what will the volume of argon be? Assume the pressure remains constant. So let me write our two equations. We have options. What equation are we going to use? Why? Yes, they gave us two temperatures, which means if you have two temperatures, you cannot use this equation because that means there's only one temperature. So I have to use the left equation. The good news, if they say the pressure remains constant, all I have to do is just remove those pressures from this equation, and I can rewrite it without those pressures. This is also Charles' law. So you can leave the pressure in. You can just say, okay, pressure is 1 atmosphere and leave it in. You'll get the same answer if you were to leave it in. It's helpful to not leave it in case you were to make a math mistake, but if you do leave it in, just pick an easy number like 1. That'd be my advice, like 1 atmosphere, because it's constant. So no matter what, if I did 1,000 atmospheres, you'll get the same answer because 1,000 will cancel out. 1,000 divided by 1,000 will be 1. But it's also helpful just to remove the constant from the equation, because you're still left with Charles' law. That way you're not memorizing Charles' law versus Euler's law, and there's an additional one with Avogadro's law, so you're not having to memorize all of those. So V1 over T1 equals V2 over T2 is the equation we would use. Let's do V for verse. So V1 is 25 milliliters. T1 equals 22.0 degrees Celsius, but it always needs to be in Kelvin. And then it says, we don't know what V2 is because it's asking us to figure out V2. And T2 is negative 18 degrees Celsius. 273.15. And I get 255.15 Kelvin. So V for verse is done. E for equation is done because we already know the equation. S would be for substitute, or sorry, R would be for rearrange. We're trying to isolate V2. So if I was to rearrange it, V1 over T1 equals V2 over T2. I could just multiply by T2 on both sides. And my V2 will equal V1 T2 divided by T1. That would be the rearrange. No, it's very small, but the Kelvin units will cancel and your answer will be in milliliters. So it's going to be the same unit that you had your other volume. If it was to say, what is the volume in liters, just double check and make sure you read the question thoroughly, because that would just be one additional step. So V2 is 21.6 milliliters. Make sure my math is correct. I'd appreciate it just because I am human. The last step, because we did substitute and solve, the last step is evaluate. So we know that volume and temperature are proportional. Is temperature going up or down comparing T1 to T2? Going down. The volume also has to go down. V1 is 25, V2 is 21.6. I know it's not that big of a difference, but it doesn't matter. It's going down. It's proportional. So evaluation-wise, this makes sense to what we know as a constant, like volume and temperature are proportional. Any questions on that? The last, wait, is this the last one? Yeah. This is the last one. Go through this one. So a chemical reaction in the lab produces 75.6 milliliters of oxygen gas. The temperature of the lab is 22 degrees Celsius, and the ambient pressure as measured with the barometer in the lab is 758 millimeters of mercury. What is the mass of the gas produced? In the previous equation, and I mean this one, is mass in there? What about in this equation? So even though it gives us N for moles, we can always figure out mass if we know moles. So the equation that we have to use for this upcoming problem is this one. One, they didn't give us two temperatures, two pressures, two volumes. So I know I have to use an addition, a new equation that would be PV equals nRT. So that's the E inverse. The V inverse would be for the variables. So I'll go through. I want to point out that R is the ideal gas law constant. And these are the units of the ideal gas law constant, and they are incredibly important. For us to throw anything into this equation, our units need to match the units of the R. So if our volume is in milliliters, do I leave it as is or do I need to do something? Yeah, I have to get my units here to match my units there. So first, go from milliliters to liters. To do that, you just divide it by 1,000, or if I was to use my dimensional analysis, make sure my units cancel. I would just move my decimal place over 3 times. 0, 2, 5, 6 liters. Temperature, 22 degrees Celsius, same concept. If my degrees are in Kelvin and the R constant, I need to make sure that my temperature is also in Kelvin. And then pressure, 758 milliliters per mercury. if you're wondering where I'm getting this equivalent from, we had it last class. 1 atmosphere equals 760 torr, which is also equal to 760 millimeters per mercury. Yep, that's the wrong number. Okay. There is one more thing I will need for this problem, but we can wait for it now, or we can do it now or later. So I'll probably wait for it to be later. So we have our V, we have our E. R will be rearranged. So if I need to figure out what's missing, I have PV, R, and T. To do that, I would need to divide by RP on both sides. That way I can isolate N. And now I can plug and chug. Just know N is moles. That's what the leftover unit is. So it'll give you moles. The units will cancel. My atmospheres will cancel, my liters will cancel, and my Kelvin will cancel. And 1 over mole equals mole. So N 0.00311. What is oxygen gas's formula? O2. Is moles the same thing as mass? So mass is a weight. Moles is an amount. Are they synonymous? Unfortunately, they are not synonymous. So the last step we have to do is convert moles to grams using molecular weight. What is the molecular weight of O2? Yes, if you go look there, it's like 15.999. So that'll round up to 16. So 16 times 2 is 32. So I don't have a lot of space, so I'm just going to come up here and write it. I want grams on top, and I want to get rid of the moles on the bottom. Where do I put the 32? At the top. That's the molecular weight of O2. And then what number do I put on the bottom? Just a 1. 32 is the same thing as 32 divided by 1. So you can leave it blank, or you can just put a 1. So this question is wonderful because we've kind of already done a lot of PV equals nRT when we did the first time. So you already are familiar with that. We did the conversions the first time, where you were asked on that worksheet we did a while ago, converting all this over. But this one combines what we've done on that worksheet with that one extra step. And it's important that chemistry is wonderful because it builds on itself. So if you are comfortable with something a while ago and you still have that in your arsenal, you can still answer a question. So we did discuss molecular weights, we discussed using these equivalents. So this question is just building off of what we've already discussed back in unit 1.6 maybe. Yeah, so it's just one additional step. So yes, you probably would have gotten majority of it right if this was a short answer problem, but don't forget that it's that step. If it asks for a mass, a weight, mole is not the same thing as weight. So you need a molecular weight to figure out weight. Any questions there? This question just requires practice. I think for me is like use verse, kind of the way we set it up. write out your variables, check your units. E, try to pick the correct equation based on the equations available to you. R, rearrange it to solve for what is missing. So even if I didn't know what n was, I know it's the only thing missing from the equation, so I can solve for the n. If I need to figure out what is the units of n, well, I can use the cancel out units to figure out those units. And then, yeah. So yeah. Let's continue putting it all together. We kind of use the ideal gas law equation to assume that the gases we are dealing with are under perfect conditions, under 25 degrees Celsius, under 1 atmosphere perfectly, but the world is not perfect. So in this class and in Gen Chem, we're going to assume the world is perfect and base everything off of that because the numbers are easy. But as you move further up in physics or chemistry or biology, the world's not perfect. And so there's other contributions that are going to affect the equation. So this is the van der Waals equation. It's just because the reality is often more complicated. This is not something that we deal with in general chemistry. I'm not trying to overwhelm you and expect you to know how to use this. I'm just showing you under non-standard conditions. So the temperature is different. The pressure is different. Maybe the amount is different. I don't know. So under different circumstances, we have to include different variables. So yeah, real gases deviate from ideal gas law under high pressure and small volumes. The van der Waals equation contains experimentally determined fudge factors to compensate for those small deviations. So this is how science is often done. It's back and forth between experimentation and theory. So we'll be using the ideal gas law, but it's important to note that we have these equations in place for things that are not under ideal perfect circumstances. So you'll be using PV equals nRT, but it is possible to do the same exact equation under non-standard conditions. Science is fun, I promise. All right. Right now, I'd like for everyone to get out the worksheet that we had from last week. I'm sorry, not last week, on Monday. On Monday, I asked you to do the first page. Now I'm going to ask you to do the second and third page. So for the next 10 to 15 minutes, we are going to work on the second and third page, and then maybe with the last 5 minutes before our break, we'll go over some of the answers. We're going to move on to atomic structure. This is going to be mostly a history lesson, so bear with me, but I do have a fun simulation to do in a little bit, and I have an M&M's activity. So if you're in person, I have some M&M's for you to eat. Yeah, yay. And I get to eat some too. I'm excited. If you have a peanut allergy or nut allergy, don't take it. All right, let's move on to atomic structure. By now, we should be more comfortable with the periodic table of elements. So this is going to have a lot of relevance to periodic table because we're talking about the atom. The atom is anything on that period that, table of elements. Each of those are individual atoms. But we're going to go into more depth on what makes up an atom. So the objectives of this section, or this 3.2, is to acknowledge that scientific knowledge changes over time. That's very important. I know Gen Chem probably in the last 25 years hasn't really changed much, but science is constantly changing. And so certain theories that we developed maybe 30 years ago or 130 years ago are constantly being improved over time with more and more science. So I think this is relevant to just everyday life, is that something that, we might have thought that was always true when we were younger might not be true because it's been disproven now. So science is always changing, and it's important to keep an open mind because, I think a good example of this is like my husband. He's from a different culture, and he has this theory that, okay, if you go outside with wet hair, you're going to get sick. That's just the way that he was raised. And even though science disproves that, and as a scientist, I'm always like, prove it. Where's the science that backs it up? Because that's not how you catch a virus. He's like, you'll catch a cold. You don't catch a virus with wet hair. And so that's because I went through a lot of science classes and I have the theory to back it up. And he's like, nope, that's my culture. That's just what I was told as a kid. So it's important to keep that open mind and say, okay, well, yeah, I was also taught that as a kid. But guess what? You don't catch a virus with wet hair. Like wet hair doesn't mean you're going to catch a virus. So that's just a way of just an everyday experience that I had to struggle with, and I'm like trying to convince my husband that science disagrees. So science definitely changes over time. Keep an open mind. And so I'm going to be doing a history lesson of how we've gone from the very first inkling of an atom to what it is now and how we got there. So we're going to sketch the history of the atomic model, including, I can't pronounce it, Democritus, Lavoisier, Dalton, Thomson, and then lastly Rutherford. We're going to describe the modern view of the atom and define and identify isotopes. We're going to connect isotope symbols, the numbers of protons, electrons, and neutrons, and of course related to the periodic table. And then we're going to end on calculating the average atomic mass of an element. So the actual average is the atomic mass that's on that table. But how do we figure out that number? And I'm going to show you how we do that. Background, this is another equation that we're not going to really deal with in our class, but it just goes back of, okay, here's an equation that's very important, even though we make assumptions based off this equation. So we talked about like attracts, oh no, we haven't hit that yet. Opposite charges will attract each other with the ionic compounds. We talked about, you have a positive ion like a metal and a negative ion, on the end like a fluorine. They attract each other to make an ionic bond. This is the same concept. So same charges will repel. If I had a positive charge and a positive charge, they wouldn't want to connect. You want to do a positive negative, whereas opposite charges will come together. Just going back to ionic bond. The reason why we can calculate that based on this Faraday's Coulomb's law. So the Faraday equals K, which is a constant. It's a Coulomb's constant. The Q1 and Q2 are the charges. So let's say I have a positive charge times a negative charge. And then the radius is important. So how far are these charges? The smaller the distance, the more likely the charges want to come together. But if I'm way over here, it might not be as easy for them to come together. So same charges repel, opposite charges attract, and then force gets smaller as distance between charges gets bigger. So you don't have to use this equation, but this equation can teach us theory and assumptions based on that. So of course, logic, opposite charges come together. If the charges are further apart, the harder for them to come together. That's just what this equation tells us. But we already have that logic down. The atom. Can we see atoms with our eyes? No. They're just too small. They're happening on this tiny little scale, and we are developing instruments that can see smaller and smaller. But the atom is just simply too small for us to see. Some bigger atoms we can see. I have a slide coming up, but like hydrogen, I don't think we're there yet. We can't really see that. It's just so small we can't see it, even with a microscope. So our scientists, even from over 100 years ago, could still make assumptions based on the atom just through theory and logic. And over time, as science has evolved, we were able to either disprove their logic or agree with their logic. So back in the day, it was mostly theory based on logic. So we explain experimental observations, we can construct theories, and then we can make predictions. And then maybe in 50 years, a future scientists can either disprove us or prove us. So Sir Isaac Newton was very important, of course. I love this quote. If I have seen further, it is by standing on the shoulders of giants. So it's just important to realize, like, even myself, like, I wouldn't be here if it wasn't for all of the science before, because I don't think if I was plopped in the 1700s, I can just do what they did. I couldn't. But their background and their theories have helped me get to where I am today. So that's why science is a constantly evolving process. And over time, we are getting better and better answers. And I love that, because even though we are at the top of everything right now, we can still find new answers and new solutions. So let's get into the history of the atom. Obviously, for your exam, I'm not going to be testing you on like the history. Do you know what year this happened? Do you know who came before who? I'm just trying to explain how we got from beginning to now. So the atom kind of started a long time ago, but we really were able to like start focusing in on it in the late 1800s. We were able to do experimentation and make theories. So between 1880 and 1945, the experimental data pushed development of the theory of the atom and cast of thousands in many labs in many countries. It wasn't just one person, it was a lot of scientists. And it really was like a race of who published the first paper to have like the first, like this last name belongs to this theory, but in reality, a lot of scientists belong to it. And it's just a tremendous story of history of science because we just built off of so much. The entire chapter 3 is the atomic. So 3.2, unit 3.2 is pretty much chapter 3. So the word origin. Democritus, all the way back in 400 BC, he had a theory that you can keep dividing everything by 2 till at some point you can't. So I know that's a very vague theory, but in reality, yes, we can keep dividing and dividing and dividing until you get to the smallest substance. And he named that one as the atmos, so meaning indivisible. At one point, you can't divide it any further, and that's atmos. So it started with him, just this idea of what can we get to, and then future science, thousands of years later, we would say, oh, that's a great idea. We proved that right. In the late 18 or 1700s, Antoine Lavoisier, he found the law of conservation of mass, which we hit on when we were doing our balancing of reactions. Mass or matter is neither created nor destroyed during these reactions. If I have 1 gram of this and it can turn into a different amount, but the atoms don't change. If I have 5 atoms of this, of carbon, in the following of the reaction, I should still have 5 atoms of carbon. You're not going to magically create new atoms of carbon, and that's just the law of conservation of mass. So going into physics and chemistry. So in chemical reactions, matter is neither created nor destroyed. Whatever your starting material is, you can create new material, but the amount of the elements are not going to change. That's why we balance reactions. It's important to have those balanced reactions. Dalton's atomic theory. So the early 1800s, elements are made of tiny, indivisible particles called atoms. And each of these atoms are unique. So all of the periodic table elements, each of those atoms, an atom of nitrogen is still an atom of cobalt is an atom, but they are completely unique to each other. So yes, every element on there can also be an atom. Atoms can join together in whole number ratios to form compounds. So we've already been hitting on it. I have carbon plus oxygen, and it creates carbon dioxide. In the previous slide, we have hydrogen gas and oxygen gas to come together to create water. So yes, these atoms can come together using either, if it's ionic, the charges, or if it's covalent, just sharing it's sharing of a bond, and it create a whole new compound. So compounds are not atoms, but atoms make up compounds. Atoms are unchanged in chemical reactions. So even though I have carbon dioxide in the products, the carbon's still the same atom. The oxygen's still the same atom. So now we're getting into what an atom is made up of. So they realized early on that an atom is mostly space. It's mostly space. There's things in there floating around, but it's just the space in between what's going around is mostly going to be space. So J.J. Thomson around 1900 kind of created this plum pudding model where he took this cake and he said that inside this cake we have little pieces of plums. Those plums are going to be electrons. Electrons are negatively charged. So the plums in here are the negative charge, and then the rest of it, that cake, is positively charged matter. Because we know that an atom is neutral. If I have an atom of carbon, we know it's neutral in charge. But electrons are going to be there, and then something else positive has to be there to make it neutral. So negative plus positive creates neutral. So this was just a general theory, and then the rest of it was made up of space. So he said that the space is positively charged, the electrons are negatively charged. His student, so this happened where the student kind of was able to disprove his theory, but still prove parts of it was true. So Ernest Rutherford was J.J. Thomson's student, and 9 years later, in 1909, he created a gold foil experiment or scattering experiment where he took a flat piece of gold and he thought, okay, well, majority of these atoms are made up of space. if I was to shoot particles at it, it would go straight through because most of it's made out of space. And so that was the theory. And Rieger and Marsden were his colleagues. They all three did it, but Rutherford, I guess he was the first author or last author, so he's the one that got credit for it. They shot alpha particles at thin gold foil. They expected to prove their advisor, Thomson's theory correct, but something changed, something different happened. So they thought, okay, so what I have here is they have the plum pudding model where you're plum pudding with the pieces of plums that are negatively charged electrons, and then the rest of it is just positively charged. They thought, okay, mostly space, it should pass right through. But what happened? So here's the setup. They have this machine that throws alpha particles through it. And over here is what the expectation was. It should go straight through. So every alpha particle should be hitting what's happening. He has this little zinc sulfide, I guess, thing in the back that is collecting what's being hit or going through it. That doesn't really matter. But these are what's happening. The alpha particles are going through the foil and hitting the back. But every now and then, an alpha particle would bounce off. That was not what was expected. So at some point, they realized that that alpha particle is hitting something and bouncing back the mirror. So what is it hitting? If we expect it to go straight through this all space, what's it hitting? And so that's where we were able to kind of figure out what else is there. So I like this quote. It says, it was about as incredible as if you had fired a 15-inch shell bullet at a piece of paper and it came back and hit you. That's what they never expected for a bullet to bounce off and hit the weak. It should go straight through the paper. Paper's weak. And so that's what kind of they discovered. This is, so here's what the original expectation was. This was created by Dr. Patterson. I think, oh no. I thought she had it in there. But this kind of just explains. So every now and then, rarely, it would bounce off of something. Here's what it bounced off of. So majority of the time, it would go straight through, and it would be like a 180-degree angle and hit the back. Every now and then, it would maybe skid off of it and then go off a different trajectory, but it still went through the foil. But rarely, it would hit something dead on and bounce back. And that little something was the nucleus, center of the atom. It hit the center of the atom and bounced back. Very rarely, but it did happen. So once they discovered that, all of these amazing chemists were able to figure out what it is. So they were like, something's there, and these other chemists were able to figure out, okay, what is that something? So Thomson, Millikan, Goldstein, I can't pronounce that, Roentgen, Rutherford, Moseley, Chadwick, a cast of thousands of scientists were able to continue and figure out all of these details. So let's skip over all of that and talk about now. Now, nucleus, the center of an atom, contains protons and neutrons. Does anyone know what the charge? If I say proton, what do you think the charge of a proton is? Positive. What about a neutron? Neutral, so 0. And then electrons are negatively charged. So at the center of an atom, we have a nucleus that contains protons and neutrons, and then they're surrounded by a cloud of electrons with a negative charge. And those electrons are continuously moving in this cloud. There's no real direction. It's floating around. And we don't know really which direction it's going to go. It's just floating. This is important. If it was drawn to scale, if I had a marble right here that represented a nucleus that had protons and neutrons, the cloud itself would be as big as Bobcat Stadium. That just shows the difference in scale of the entire atom to just the nucleus. It's a marble inside of Bobcat Stadium. That's why the theory proved that majority of the time it would pass through that electron foil or that gold foil because it's mostly space. But maybe one in every 20,000 would hit that center and bounce back. I mentioned this. I know we have come so far. This is from 1989. So we weren't able to see an atom or even move atoms up until the 1900s. But this was in 1989. Some scientists, I think from IBM, they were able to use a scanning tunneling microscope at a very, very small level to put xenon atoms in order. They created this. It says IBM, made from xenon atoms. So yeah, we've gotten to a point where we can see certain atoms, I mean, not every atom, but science has just come so far from the theory of atoms to being able to see atoms. Now let's talk about what we're going to be doing. So you can see the previous exams, it's not going to be like a history lesson. Maybe I might mention it, but it wouldn't be majority of your exam. We're going to get into what you might see in the worksheet and the exam. Atoms are made up of protons, neutrons, and electrons. Protons go in the nucleus, and they generally have a mass. AMU just represents atomic mass units. Spell it out. And they represent about 1 atomic mass unit. Same thing with the neutron. They're so similar that typically we kind of assume it's the same mass. Electrons are so much smaller. They're so much smaller. Look at the number here compared to 1. They're tiny. So majority of the weight of an atom is going to come from the proton in the nucleus. We don't really, neutron. We don't really assume the weight is being contributed by the electrons. They're important for charge, but they're not affecting really the mass. All right, we're going to get into isotopes. Now, atoms can exist in different, can be the same element, but have different weights. So here's an example of hydrogen. What we see on the periodic table of elements, we kind of already been assuming it's this one. So the mass of hydrogen based on there, it's around 1. So in this one, the mass number is this number up top. That tells you the weight of this isotope. You can assume it's 1 gram per mole or just 1 atomic mass unit. The bottom number here, this atomic number is how many protons are in this isotope. It's also the number on the periodic table of elements. So hydrogen, top left, the atomic number is 1. So it's 1. So that atomic number represents how many protons are in the center. So if I was to ask you how many protons are in bromine, how many protons are in bromine? 35. Yeah. So it's kind of wonderful how they did that, because I don't have to count or have to make assumptions here. All I have to do is go find the number on the periodic table of elements and say, that's how many protons are always in this element. Hydrogen will always have 1 proton, always. For it to exist as hydrogen, it needs to have 1 proton. The neutrons can change. The electrons can change, but it will always have 1 proton for it to be the identity of hydrogen. So if I go switch over to this next isotope here, I still have 1 proton of hydrogen, but I have an additional neutron in there to give it a little bit extra weight. So it's double the mass. So at the center, I have 1 proton and 1 neutron. This isotope of hydrogen will be 1 proton. That's never going to change, but it has 2 additional neutrons. So that, remember that 3 that's up top, that 2 that's up top, that's just the weight of it. So I know how many protons, you can subtract whatever's left over is how many neutrons. And then the bottom number is not going to change. The top right here just shows you that all of these will have a specific number of electrons. The electron does not affect the weight. So regardless of what it'll maybe affect charge, it's not going to affect the weight. Any questions on that? I know this is new. So versions of the atoms of an element with different number of neutrons cause different numbers of weight. Now, in reality, each element has a favored one. So everything has isotopes, but there's always going to be 1 majority. So if I look at hydrogen, this one's going to be the majority, in the majority. So every element will have 1 of these isotopes that is going to be 90%, 80% of that in existence. But the other ones do affect the weight. So there are different masses and different mass numbers to reflect these different isotopes, but the protons will never change. That bottom number never change. It has slightly different properties. So let me just go back. if you are in organic chemistry, they do deuterium a lot when they're doing certain chemical things like using NMR. Tritium is also an isotope of hydrogen. These are very rare. Majority of hydrogen is going to be a protium, the name of that isotope. So it just depends on where it's happiest. So majority is going to be this one. I'll explain how I know that in a little bit. So protons, that's all going to be the atomic number in the top left corner of that periodic table of elements. It will never change for the elements. So if I was to change the protons and go from, let's say, 6 protons to 7 protons, I'm completely changing the element, going from carbon to nitrogen. But if I'm only focused on one thing, hydrogen, they're all going to have the same number of protons. Okay. Let's look at the PhET simulator. These are fun. So when you have like some downtime, or if you want to do it with me now, here's the link. But if you just Google PhET and build an atom, this is what comes up. But this kind of helps me at least visualize what's going on. So remember that the proton tells you the identity. If I was to put 1 proton in here, the identity is the number 1 element on the periodic table of elements. If I wanted to put 6, notice how the identity is changing every time I add 1. So regardless of what's happening with neutrons and electrons, the identity is all based on protons. If I start putting in, I'm gonna add this, is it stable or unstable? Stability just tells you where it's happy. Right now, as I'm building it, there's just not happy right here. But you can see that this is changing as I'm adding neutrons. So the proton represents the identity, represents the number on the periodic table of elements. This represents the weight, protons plus neutrons. So sometimes I might give you and say like how many neutrons are in there. If you know the protons, you can always subtract them. So right now I have 6 neutrons in here because I know I already added 6 protons. If the weight is 12, 12 minus 6 is 6. Okay. Electrons, how many electrons? 3. So you can see it's telling you the charge here. Electrons are negatively charged. If I take one out, it's just you taking out 1 negative charge. That's why it's a +1. If I add more in, now I have an extra electron that's giving a -1 charge. So these are really fun to play around. Let's make beryllium. Look at beryllium, it's Be. How many protons should I add? 4. Okay, now I have beryllium. What is the weight of beryllium? You can see. Should be, yeah, around 9. So what number of neutrons should I add? Okay, now it's stable. Electrons, I'm just going to do it until it's neutral. Okay, now it's neutral. So we've created a stable beryllium atom using this. Let's now make. I'm going to kind of ignore the orbits right now. Let's just switch to clouds. Yay. Okay, so I can. So it's neutral right now. See this charge. If I take this out, ooh, beryllium. What charge does beryllium have if it was an ion? So look at the periodic table of elements. What column is it in? The second one. So typically, if it's an ion, it'll have a 2+ charge. This is what beryllium ion looks like if I was to write it as an isotope. Beryllium can exist, you know, or no, it doesn't. It says unstable, it does not exist like that. Maybe if I add, nope, beryllium is just wants that many. Yeah. There you go. We built a beryllium atom that was neutral. We built a beryllium atom that was its normal ion if I was to have an ionic compound. Let's do oxygen. How many protons? 1, 2, 5, 6, 7, 8. What is the weight of oxygen? 16. So how many neutrons? 2, 3, 4, 5, 6, 7, 8. Yay, it's stable. I'm going to add electrons. Oh, oxygen. What charge does oxygen want to be if it's an ion? 2 minus. I'm going to add until there's 2 minus. That means I have an extra electrons there because it has a 2 minus. That's happy oxygen when it's in a 2 minus ion state. If it was neutral, you just take those 2 additional electrons out, but it's still oxygen. This is a lot of fun to play with as we're learning. Some of these elements aren't going to be able to round up. So oxygen is 15.999. So it pretty much rounds up to be 16. It's not always going to be a perfect number. Sometimes the number might be like something 0.5. That tells you the isotopes. So if it rounds up to be 16, then majority of oxygen are going to look like this with the 8 and the 8. But sometimes it can't exist when they have slightly less. Do you have any questions about this? This is a lot of fun. I think this, as you're learning, this is a lot of fun to play with, to kind of say, okay, what is contributing to this top number? What is contributing to this bottom number? And this tells you charge. Let me switch back over to our slides. We're going to do a little bit of math, so you'll need a calculator, but this is kind of leading up into that we're about to use. Just a little challenge. If I was to give you a percent, could you write the decimal to represent that percent? How do you go from percent to decimal? You just divide it by 100. For me to figure this number out, 50% is if I took 50 divided by 100 times 100. So you just take a number divided by total. You know, that's how you create a percent. You have a certain number, you divide it by the total amount of something, and then you multiply it by 100. But if I want to get rid of the percent thing here, you just divide it by 100. So go ahead and turn these numbers into decimal places. If you can't do it in your head and divide it by 100, you can always just use your calculator. What's 50 divided by 100? 25? 0.5. 0.25? 5? 0.12? Yeah. So when in doubt, use your calculator. But if you can, you just divide it by 100. It's going to be relevant when we do the next step because isotopes happen in percentages. So maybe 90% it exists like this, 2% exists like this. So we need to know the decimal place of these percentages if I give you percents to do this math. So it's average atomic mass. If I look at the periodic table of elements, nothing is purely a single number. Everything has decimal places. If the world was perfect and every element existed by itself as one isotope, none of them would have decimal places. But each element exists with different isotopes. Certain percentages will change things, and that's where those decimal places are coming from. So I mentioned, how do I know what is the most common isotope? I can kind of see, okay, where is it closest to? So if you look at hydrogen, the number is 1.00 something. So that tells me that since the number is closer to 1, majority that are in existence is going to have a mass closer to 1. So that's H. 0.11 is the most common isotope since it's so close to that number. If it was maybe around 0.5, so 1.5, then it would be like a 50-50 shot of it being something else. Oxygen's another one where the majority existence is one thing. So if I have oxygen that's like 15 and 8 versus oxygen 16 and 8, look at this number. It's closer to 16. So majority of oxygen isotopes are going to be that one. So that's how they were able to calculate this based on doing a little bit of math. So elements naturally occur as a mix of isotopes. Each isotope has a slightly different mass. And if you need a mass for the element, the best one to use is the average of all of the isotopes, isotope weights and the percentage that exists. Yeah. This is that equation. So if you have 3 isotopes, you need to take the sum of each isotope, where you're taking, okay, your decimal abundance, which is that percentage turned into a decimal place, times the weight of that isotope. So that would be that top number. You'll have to be given the other number. So if I give it to you, can you calculate it? I wouldn't round these numbers until the very, very end. So I'll show you what I mean. Find the average atomic mass of neon. So we actually can compare our answer to the true answer that's up there. So we need to figure this out. There are 3 different isotopes, so we need to kind of take into account the decimal abundance and the isotopic mass. So let me add another column. What is the decimal abundance? So what's 90.48 turned into a decimal place? All right, next one. All right, next one. Perfect. So you need to have that number, and then you need to have the atomic mass value. So let's do the setup. So average atomic mass equals, it's the sum. So I need to take decimal abundance. Let me see the word. It was decimal abundance times isotopic mass. So for neon 20, I'll need these 2 values. So 0.9048 times 19.99244. Don't round until the very end. And I put it in brackets because I just want to make sure, like, I know this is neon 20. Okay, and then when it says sum, you're adding them all up. That's neon 21. And then I'm going to add it here. 21.9. And then add them all. Calculate this for me to get the average. It should be very similar to the neon up there. That's how you can check your answer. Then it's do the M&Ms. Go late. Oh, we're glad they're promised. Yeah, one additional bag. I made 5 bags. So if you want to take some random stuff. Hopefully you got 20.118. I'm going to switch over to a new worksheet and pass this out. It's the average atomic mass worksheet. We're not going to have time to finish the whole thing. Maybe we can come back next class and work on it a little bit. But I do want to do the raw downs. So you can kind of answer the first one. You can answer it when you have some downtime. But let's skip to the raw data portion. Maybe next class we'll start off by finishing the rest of the worksheet. I'm gonna take a look at the back while I'm doing all of this setup. See if you can answer some of those questions while I'm doing this. I'm going to be relating M&Ms. How does it go? I'm going to be relating M&Ms to isotopes, and particularly I have two. So the two that I picked are these dark chocolate M&Ms and peanut M&Ms. They look very different. They have different weights, and it's relevant to like assuming they're isotopes. If I was, I do want to point out on here is this is a regular kitchen scale. I didn't clean this. I'm telling you now, I'm a very messy cook. It's probably covered in flour because I just made pizza dough on Monday. So the best way to do it is you always want to put a clean thing. So if I want to eat these M&Ms, I'm not going to ever put anything directly on a scale. Never trust the chemist in front of you. I'm going to put a cup on there, and I'm going to press this 0 button because I want to have the accurate mass of each individual M&M. So let's start with this dark chocolate. If I put one in there, why can't my scale read it? It's not heavy enough. The scale is just too small. Treat that like an atom. Atoms are too small for us to weigh, but if I have enough of them, if I have a mole of them, I can weigh it. So this is, I'm going to pretend like, you know, it's like a real element. It's a real atom. It's just too small. But if I pick a number that's whole, let's say 10, maybe I can get a better weight. So 1, 2, 3, 5, 6, 7, 8, 9. So 10 of these elements are going to be, or isotopes are going to be 8 grams. Oh, 7 grams. So where it says on the page 1, where it says isotope right here, I want you to put DC for dark chocolate. So dark chocolate, you will put right here. Isotopic mass, you're going to put the number of each individual. So if I have 10 of them that weigh 7 grams, how much does each individual weigh? 0.7. So I just take the 7 grams and divide it by 10. So DC, 0.7 grams. The percent abundance, each of y'all, we're going to get a different amount because it depends on what's going on in your bag, and I did not count. But I'm going to skip to the next one. Let's do this one for peanuts. Just do PC for peanuts. I'm going to weigh another empty cup. These are bigger. So I'm going to also weigh out 10 just to be consistent with the other one. Definitely have it start at 0 before I start. So this one's bigger, but I want to be consistent because each of these M&Ms, if you were to look at the bag, they look so different. So 10 of these weigh 25 grams. So on my paper, I need to put the exact weight of each individual. It's an average because they are so different. Some may be 2 grams, some may be 3 grams. So what is the average of each individual piece in here? Yeah, 25 divided by 10 is 2.5 grams. So what I want you to do now, if you are in person, is count how many peanut M&Ms you have. They're the big ones. And how many dark chocolate M&Ms do you have? Calculate your total. Sorry, I gave you extra. If I was in a bigger class, I would have given you very little. And then if you're online, I'll grab one of the baggies and do it with you. So we need to calculate our percent abundance. That's taking a number divided by total. So that's 2 peanuts. And once you're done counting, you can start eating. You want to like write down total, or, you know, write somewhere how many of each you have. I think that's all of the peanuts. So I have 1, 2, 3, 4, 5, 6, 4. I have 16 peanuts. Then how many dark chocolate I have? I have 1, 2. Forgot it. I'm gonna eat this peanut because I don't feel like recounting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15 should be. So for me, 18 plus 6. Do that math in my head. It's like 30. 34. Yeah. So that's how I kind of do it. You take your individual ones divided by your total times 100 to get that. So you need to go ahead and calculate your average atomic mass using the equations. That's the sum of decimal times mass. So you take this number times this number in parentheses, plus this number times this number in parentheses. So you can see how each student will have a different number. So go ahead and calculate that. When we come back into class on Friday, I'll probably kind of put this together and we'll start from there. But thanks for showing up. Yeah. But yeah, we'll probably continue working on this next class, but I want to get the M&M fun out of the way.